I am Dr. V. Himamaheswara Rao, Assistant Professor of Physics, Department of Freshman Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Welcome to the lecture series Atomic and Molecular Spectroscopy. Here we are going to discuss the topic spectroscopic terms by using the Breit scheme. So we already, in our earlier lecture, we already discussed the procedure to find out the spectral terms for equivalent p electrons when there are two electrons in the p subshell. So let us find the spectral terms by using the Breit scheme. So in this scheme, for example, whenever we are considering the configuration p2, that means two electrons in the p subshell. So in this scheme, we will arrange the table for indication like this. So P2 means there are two electrons in the p subshell having L values. That means L1 equal to 1, L2 is also 1, as the two electrons are in the same subshell P. So for P, L value is 1, the two electrons are in the same p shell, so L1 is also 1 and L2 is also equal to 1. So here the possible values for first electron, p electron, as L1 equal to 1, ML1 values can be 1, 0, minus 1, and the possible values ML values for, they are indicating this as ML2, and the possible values for ML2 is also 1, 0, minus 1, as L2 equal to 1. So here in this scheme, we are writing ML1 values onto the right side like this, 1, 0, minus 1. And ML2 values vertically we are writing like this, 1, 0, minus 1. One set of values horizontally, one set of other set of values vertically to the right side of ML1 values. Now we need to add, whenever these are the ML1 values for one electron and these are the ML values for the second electron. So whenever there are two electrons in the same subshell, so based on the ML values, that means particularly the ML values indicates the orientation of electron orbit around the nucleus of atom. So there could be different states of electron. As there are two electrons can exist in different states. So different combinations of states are possible for those two electrons. So that whenever two electrons are combinedly revolving around the nucleus in different states, they can have different ML values. So we need to add up the total orbital angular magnetic quantum numbers, so that these are the ML values for one electron, these are the ML values for second electron. So we need to add up ML values for obtaining the combination of the two electrons. That means whenever the two electrons are combined based on the state of our ML values, we can obtain total orbital magnetic quantum number like this. So whenever by adding 1, 1, 2, So 0 plus 1, 1 minus 1 plus 1, 0, and again whenever we take 0, 1 plus 0, 1 here. So we are writing all these values to the left side of ML2 values like this. So 1 plus 0, 1, 0 plus 0 here, 0 corresponding position, 0. So minus 1 plus 0, 0 minus 1, and 1 plus minus 1, 0, 0 plus minus 1, minus 1, minus 1, minus 1, minus 2. So these are the values after adding ml values of first electron and ml values of second electron individually. Okay, so here we can see the total orbital angular momentum values, ml values starting from 2, 1, 0, minus 1, minus 2, like this. So this row, this particular values 2, 1, 0, minus 1, minus 2 forms D term. And if we see this column, this values 1, 0, minus 1, these particular ml values represent the P term. And here in this 0, ml value 0 indicates the P term. So this is the uh, representation or procedure to follow the finding the spectral terms for two electrons which are having L1 equal to 1 and L2 equal to 1, in which those two electrons are in the same subshell. So here we can form, these are the combination of different combinations of electrons, those can be existed for the two electrons. So if one electron is in this particular state A, the second electron must be in the any of the other combinations, not the same state A. So we already discussed that there are 15 combinations, 15 possible combinations for the electrons to be existed in any of the combination. Those two electrons can be existed in among any 15 combinations, any two of the 15 combinations. So here, whenever we see okay, so these nine values, if you see, there are 9 values for the total orbital angular momentum ml. So there are 9 values. So we can divide these 9 values into 3 sets. 3 sets L-shaped dots. There are L-shaped dots. So this is one set, second set, third set. So there are 3 sets of ml values. So the first set is 2, 1, 0, minus 1, minus 2. 2, 1, 0, minus 1, minus 2. This is the first set. And it indicates D term. And the second set 1, 0, minus 1, 1, 0, minus 1. This is the second set. So 1, 0, minus 1, that indicates L value 1, total orbital angular momentum, L value equal to 1, that means P term. And the third set Oh, we should not indicate like this. First, let us find out the three individual sides. So the third side is 0, only 1 ml value, and this is the third set. So this is the first set, second set, and this is the third set. There are three sets of ml values according to Breit scheme. So these values, particularly whenever we observe, that means there are nine values of nine ml values are possible by taking the combination of the two electrons having different ml values. Okay, so the value 2, we are obtaining the value 2 for ml when ml1 is 1 and ml2 is 1. So ml1 and ml2 are same for the two electrons to obtain the 2. And here also, to obtain 0, the ml1 value is 0, ml2 value is 0. That means two electrons having the same ml values. And minus 2, this value we are obtaining when ml1 is minus 1 and ml2 is minus 1. Both ml1 and ml2 are same for the two electrons. So these values are obtained whenever both ml values are same for both electrons. That means ms value must be different because ml values are same for the two electrons. Already we are taking the two electrons which are in the same orbital. That means principal quantum number is same for the two electrons. N value is same. And again, those two electrons are in the p shell. For p shell, L is also same. Okay, so N is same, L is same, and these values are obtained only when ML are same. The values of ML are same. Then MS value must be different. Okay, so MS value, as we have seen here, let us see here MS values. Whenever two electrons, whenever two electrons having two electron combination, one electron may be 1 by 2, second electron 1 by 2, then first electron 1 by 2, second electron 1 by 2, then the possible total spin quantum number S equal to 1. Then that means when S equal to 1, MS value is also same. This type of combination is not possible because with these values, particularly with these ML values, total orbital angular momentum values, these MS values are not possible. That means whenever S equal to 1. So when S equal to 1, we should not take these diagonal values. Okay, these diagonal values. So that these values 2, 1, 0, minus 1, minus 2 indicates SS. Here, as we mentioned earlier, this is representing the D term, 1, 0, minus 1 representing P term as L equal to 1, and S, this is the term S. This indicates the term S. So those ML values in those three sides, L is equal to L 2, 1, 0 respectively. So that means 1 D term, 1 P and 1 S term. Okay. So whenever the two spins, we are here in this diagram, we are adding only ml values whenever we need to add a spin magnetic momentum. So when two electrons can be combined to form total spin angular momentum 0, so we can combine the two electrons to form s equal to 0 or s equal to 1. Any possible combination uh, gives two values, s equal to 0, either s equal to 0 or s equal to 1. That means s equal to 0 means singlet and s equal to 1 means triplet. So as we discussed in the earlier slide, for s equal to 1, both the electrons have the same spin quantum number ms. Okay, and hence they must differ in their values of ml. But for the diagonal, diagonal the values lying in the diagonal are obtained only when both ml1 and ml2 are same. So this combination is not possible for s equal to 1. So whenever s equal to 1, that means the two electrons having the values ms equal to 1 by 2 and ms equal to 1 by 2, you should not take the diagonal values. Okay, so if we remove these diagonal values, the remaining, either in the downside or upside values, that means 1, 0, minus 1, that forms uh, one side of the diagonal. Okay, it corresponds to the values for s equal to 1. For s equal to 1, the possible L values or ML values are 1, 0, minus 1. That indicates the second set. See here, thus with s equal to 1, we are limited to the values 1, 0, minus 1. That indicates second set. So the second set forms with s equal to 1 and l equal to 1, it forms the term 3p as s equal to 1 multiplicity m equal to 2s plus 1, that is equal to, as s equal to 1, 2 into 1 plus 1 means 3, and for l equal to 1 means the term is p. So 3p is the term representing the second set. And we can also find out the j values. If s equal to 1, l equal to 1, j values can be obtained by l minus s to l plus s in integral steps. So 1 minus 1 to 1 plus 1, that means 0, 1, 2. So these are the j values. So the final spectral terms, fine spectral terms 3p 0, 1, 2, corresponding to the second set of values, ML values. Whenever we consider possible S value is 1. Okay, so when S equal to 0, that means S is 0 This value is obtained only when the two electrons having opposite s values. One s value is 1 by 2 and the second ms value is minus 1 by 2. So 1 by 2 minus 1 by 2. The combination should be 1 by 2 and minus 1 by 2. That means total s value is 0. As the two electrons are having different ms values, so that ml can be same. ml value can be same. From the above diagram you can see, even from this diagram. This is already taken, completed, forming the term 3p012. So remaining ml values, this set or this set. So first set and second set are possible with s equal to 0. This set and this set are possible, and this set is possible only when s equal to 1. So this set particularly forms D, and this set is third set is forming as L equal to 0. The term is S. Okay. So here the term is D. Here S value is 0, and here S value is 0. So here if you mention, so L values, possible L values are 2 and 0, and possible S value is 0. So the possible terms with L equal to 2 and S equal to 0, that means singlet. The terms are singlet. So 1, 2 means D, 1D. And here L equal to 0 and S equal to 0 means multiplicity is 1, and L equal to 0 means 1s. So for the corresponding remaining two sides, we are obtaining the terms. One is 1D and the second one is 1s. So now corresponding to those three sides, we are obtaining the spectral term 1s, 1d and 3p. And we can find the j values also. For this 1d, as s equal to 1 by 2, multiplicity 1 means s equal to 0. s equal to 0 and l value is 2. So the j value must be 2. And here as l value is 0, s value is 0, j value is also 0. So 1d2 and 1s0 are the corresponding terms. So 3p, 3p find spectral lines 3p012. So these are the spectral lines we are obtaining from Breit scheme. And as we discussed in the earlier lecture, for equivalent configuration, electron configuration, the spectral lines are spectral terms. These spectral terms are same for those of the P4 also. So P4 electron configuration is also having the same spectral terms. So P2 and P4 both having the same spectral terms. So this is the procedure to find out the spectral terms following Breit scheme. In the next lecture, we will see how to find out the spectral terms for two or more D equivalent D electrons. These are the references. Thank you all.
Like, share, and subscribe. Hit the bell icon for more updates.